is going to be part 11 of the collective communication in MPI. So we're going to continue from where we left off. We actually sort of saw MPI all gather in it. Now the next one on the line is MPI all gather V in it. So MPI all gather V in it. Again, I always forget this .c here. I go slowly again so that you can see everything. Basically, this count and the request is added here. We have the initialization phase, again, this cycle of starting and waiting. And then since we are having only one request handle, you have to make sure that it's freed in order to use it in another collective persistent communication. You do the cycle again for the C style strings, and finally you print the results in rank 0 and rank 1. So let's do MPI CC MPI all gather V init.c. Then you run it with 4 processes. Oh, this has to be running with 8 processes. Okay, that's what we get. The next one on the line is MPI all to all init. So MPI all to all init.c. Wait a second, did we go with... Yeah, we forgot to go with MPI all gather V init, the inter-communicator case. We forgot to do that one. I go again slowly. The only things added is the request and the persistent count. Again, everything is the same. Then we have the initialization. Then we have the cycle of starting and waiting. And then group A prints the results, group B prints the results, and then finally you free the resources. MPI CC MPI all gather V init inter-communicator case. You run it with 8 processes, you get these results. All to all init. Again, I go slowly. Everything is the same. You have this persistent count and the request handle. You initialize. You do the cycle of starting and waiting. You free the request since we have only one. We are using only one request handle. Before using it for the CSLI string, you have to free it. You do the cycle. And then finally print the results in rank 0, rank 1, and rank 2. So MPI CC MPI all to all init.c pay run minus np4 a.out. Oh, it says 8 we have to use. Yeah, this is what we get. And in the case of MPI all to all init, the inter-communicator case, I go slowly. This is the initialization step. This is that cycle. And then again, here we only have the integer buffer. We don't have the C style string. And let's do MPI CC MPI all to all init inter.c and MPI run minus np4. This is what we get. Now we go to MPI all to all v, MPI all to all v init. Again, I always forget this .c in the end. I go slowly again so that you can pause the video and check the code, but everything is the same as the blocking and non-blocking counterparts. We have the initialization phase. We have the intra-communicator. The info handle is null, and then we pass in the request handle. We have the cycle of starting and waiting. Since we are using one request handle, again, for the C style strings, you have to use the You have to free the request and then use it in the persistent collective communication. Do the cycle again. And finally print the results in process 0, process 1, and process 2. Okay. PCC MPI all to all v init.c, and you run it with 4 processes. It needs 8. This is what you get. Actually, I don't know why did I put 8 here. So this should be, if it's less than 4. So, oops. Let's go with MPI CC, MPI run. Yeah. Okay, now it makes sense because here you see that the output is a little bit cryptic. Yeah, there's something wrong here. But then with that change now with 8 processes, it works completely fine. So let's do a safety check. So we haven't done anything wrong. So the next one on the line is the MPI all to all v init, the inter-communicator version. I go again slowly. Everything is the same. We have this persistent count and request handle. And then you have the initialization phase with all to all v in it. And then you pass in the intercommunicator. That's the significant matter there. And then your info null. And then the request handle, you do the cycle. And then finally, you do stuff here. And of course, this comment here in place for char star strings, this is something extra. We don't have any char star strings here. We only have the integer buffers. That's what happens when you copy and paste. MPI-C, MPI all to all v init inter, and we just run it. This is what we get. Again, if you don't know what these mean, please go back and watch the blocking versions of collective communications. Then you basically know what is the semantics of these stuff that I'm talking about. I mentioned it, I re-stress basically these things over and over because I want to make sure that if you start watching from this, for example, part to check out this stuff, then you know that why we are going so fast, because we already covered these material. I don't want to spend too much time on these. Next one is all to all W. This gives you the maximum flexibility. MPI all to all W in it. Again, I go slowly. Oh, we have the same issue here. We can use the size less than 4. And there we go. We only have this one and the request here. And we have the initialization phase, do the cycle, and since we are using one request handle, make sure that you free that before using it for the CS style strings. For the CS style strings, we are using the MPI in place. Then we do the cycle again. Then finally in root rank and in rank number 1, rank number 2, we print our results. So MPI CC MPI all to all W init. Let's see, you run it, and this is what you get. And in the intercommunicator case, all to all W init inter. I go again slowly so that you can pause the video and check the code, but everything is the same. No magic is happening. We only have the persistent count and the request handle. These we have discussed in previous videos. I'm not going to comment again. We have the initialization call. Here the significant matter is that we are using inter-communicator. Do the cycle. Again, group A are going to print their results. Group B is going to print their results. So let's go with MPI CC MPI all to all W init inter, and then MPI run. This is what you get. And finally, we have the reduce operations for persistent calls or operations. So MPI reduce init. We need to hop back. We need to go to reduce ops, and we need to go to persistent. And here again, do a safety check. Whoops. And the first one is MPI reduce init. MPI reduce init. I'm going to go slowly again. This is a very simple example again. Reduction operation, you initialize, you do the cycle. It's a dummy one, but just see the syntax and the semantics, how it works. That's what matters here. Reduce init.c, and you run it. With 8 processes, it's going to be 28 because we are doing a summation. You can also check the MPI reduce init in the case of inter-communicator. I'm going to go slowly again. The only difference is you have the persistent count and you have the request handle. And then here you pass in the inter-communicator, the info null, and the request handle. You do the cycle, and then you print the results. MPI CC MPI reduce init inter. And then we run it. This is 22, and that's what we get. So if we make it 4, it's easier for us to understand. That's going to be 5 because group B has the processes 2 and 3, and the summation of 2 and 3 is going to be 5. Easier to understand. We have all reduce here. We have MPI all reduce init.c. I'm going to go slowly again. Initialization step. We have the persistent count, request handle. Everything is the same. We have the intra-communicator, do the cycle. Rank 1 and rank 0 are going to print the results. I made a mistake here. MPI CC, MPI all, reduce init.c, and then we run it with 4 processes. Summation is going to be 6 for every process. And now all reduce init in the inter-communicator. We're going to work with the roots in process A and the members of group B. Go slowly again. Initialization phase. This time you're using inter-communicator instead of MPI comworld, and do the cycle, then print the results in group A and group B. MPI CC MPI all reduce init inter-communicator case MPI run. Again, 2 and 3 summation is going to be 5, 0 and 1 summation is going to be 1. Next one is reduce scatter block init. Reduce scatter block init.c. I go slowly again. Initialization call, do this thing, the cycle, and then finally print the results. MPI CC, MPI reduce, scatter, block, init.c. Here the size of the blocks that you are getting is the same. Then you have the case for MPI reduce, scatter, block in the inter-communicator case. I'm going to go slowly again. You can pause the video and check, but everything is the same. We just have the persistent count, the request handle. You initialize it, you do the cycle. Then you, for group A, you print stuff. For group B, you print stuff. You free the resources. You do MPI CC, MPI reduce, scatter, block init, inter-communicator case. You run it with 4 processes, and these are the results you get. You see the difference here is 6 and 5. This is 6 because 0, 1, 2, 3 is summation is 6, and this is in group A involves the stuff in group B, which is 2 and 3. 2 plus 3 is going to be 5. Group B starts with process 0 and 1. Summation is 1. That's how we get the difference basically in these two. Then we have reduce to scatter, which gives you flexibility to have different sizes for the blocks. MPI reduce scatter init.c. I go slowly again. We have the persistent count, the request handle, you initialize, do the cycle, and then print the results. PICC MPI reduce scatter init.c. Then we run it. We get this result. I know that everybody gets 4 because our blocks were 4 equally sized, although that we can use different sizes. And in the case of reduce scatter init and then inter-communicator, then I go slowly again. Everything is the same. Then you have initialization call with the inter-communicator and the cycle. Group A prints the results, group B prints the results, and then you free your resources. MPI CC, MPI reduce, scatter init, and then inter-communicator case. Whoops, MPI run. This is what you get. In group A, 2 plus 3 is going to be 5. In group B, 0 plus 1 is going to be 1. And next one is the inclusive scan. So MPI scan init. We don't have any sort of inter-communicator. It always works with intra-communicator. You do the cycle. This is the scanning. We have seen it for the blocking ones and non-blocking ones. So we do MPI CC, MPI scan init. We run it. And again, we get this prefix, basically the prefix sum. And finally, is that the last thing? Probably this is the last thing that we have. Access scan init. So everything is the same. We just use the exclusive scan, initialization, do the cycle of starting and waiting. And finally, the most important thing is that process 0 has undefined behavior if you try to access those data, because this is an exclusive scan. It doesn't contain the rank that you're working with. So that's the importance. MPI X scan, and then we run it, and this is the prefix sum that we get, which is consistent with the other versions of it. Okay, there is some correctness stuff. There are some examples of erroneous codes and stuff like that, which you can basically read yourself. It's a very sort of short section. You can read it by yourself. There's nothing, no significant, let's say, communication pattern or anything here. So basically we finished chapter 6, which was collective communications. Again, some final remarks is that we have covered in an exhaustive manner basically all the blocking, non-blocking, and persistent collective communications. Along with those reduction operations, we put emphasis and we sort of separated these blocking collective communication patterns with the reduction operations, because those reduction operations, to me, they have another significance. They're important. And that is why we had two separate sort of directories. So here we had blocking, non-blocking, and persistent. And then for reduce operations, we had a separate directory. Starting from part number 6, let me check. Starting from part number 6, we talked about reduce operations. So in the first 2-3 videos of these parts, so part 6, part 7, part 8, possibly we have more explanations of the syntax and semantics. But then after that, when we come to non-blocking communications, then we go blazingly fast. And the reason for that is because that we have covered all the syntaxes and semantics in blocking counterparts. So if you don't understand, if it's too fast for you, please go back and watch the initial parts of collective communications in MPI. And that's it. I hope you learned something from this video. We'll be back again.